Hello, everybody. So today we're going to talk about some operations related to manipulating differentiable forms on smooth manifolds. So as a brief outline, we're going to first discuss differential forms over a vector space pointwise, and then we'll talk about when we set these on a differentiable manifold, what that looks like on a local level, as well as globally on the manifold. Then we'll talk about some operations that make sense on differentiable manifolds, without the assumption of a metric in addition to just the data of the manifold. And then we'll add the data of a metric and talk about differential forms in the context of geometry. Okay, so we'll start with a brief review of what a tensor is. So say we have a vector space, we have vectors, and then we have dual vectors. What a tensor, a PQ tensor is it maps P dual vectors and Q vectors to the real numbers for a tensor over R. Right. So it's taking these and mapping them in a multilinear manner to the real numbers. Right. So in this sense, a differential form is just a specific type of tensor where we are only taking vectors as arguments. We're going to take q of them, and this tensor is totally antisymmetric. So if we swap any two of the arguments, we get minus the answer that we had previously. Right. So that all makes sense for some particular vector. Space, and then we can talk about differentiable manifolds. This is a very heuristic definition, but as opposed to our space just being Rn, now we want a space that locally looks like Rn, but globally may have some different structure. So we can formalize this a bit by covering our space in charts, which structurally look like Rn. These are called coordinate systems. And then if we have a smooth manifold in the intersection of these charts, the coordinates basically have to behave in a specific way, which is related to smoothness of functions in the sense of calculus. So this is very heuristic. But the point is, for one of these differentiable manifolds, we naturally get a vector space at each point in the manifold. And this is what will be relevant for our discussion of tensors and in particular differential forms. Okay, so yeah, as I said, now we can define differential forms on our manifold pointwise over the tangent spaces. So within a particular coordinate system, so locally on the manifold, we could write these in terms of the coordinates, but we can also make sense of differential forms globally. So on the intersection of these charts, these need to fit together in a smooth way. So what this means is that locally, we could write these out in a particular coordinate systems. Smooth means the component functions when we write these out in the coordinate systems are smooth in the sense of calculus. Okay, so now before we get into discussing operations on differential forms that involve a metric, we have some fundamental operations to discuss. The first one of these will be the wedge product, right? So essentially we start out with a differential form of rank P and a differential form of rank Q, and we want an operation which can be used to construct a differential form of degree P plus Q, right? So essentially what this is going to do is this is going to multiply the components, but do it in a totally anti-symmetrized way, such that the resulting thing is necessarily anti-symmetric and therefore a differential form. Right, so this is the expression for this in terms of vector arguments. And then in a particular coordinate system, we could write out a differential form alpha as such. And this is what would be called writing it out in terms of components. So for a smooth differential form, the alpha I1 to ik needs to be a smooth function of the coordinates. Right? And just at the pointwise level, we can make some comments about the possible degrees of these differential forms. So if this is an n-dimensional manifold, just based on the anti-symmetry of this, we could see that a differential form can't have degree greater than n. That would force it to be 0 identically. And we can actually write down expressions pointwise for the dimension of the vector space of differential forms of rank P over an n-dimensional space. Okay, so in addition to the wedge product, we have the exterior derivative, and this is going to be an operation which sends a k form to a k plus 1 form via the expression below. So this hat operation here means in this particular term, the sum omit xj from this. This will make sense in terms of the number of arguments that the beta should have here. And then vectors on differentiable manifolds act on functions. This is how they're defined, and that's what this notation means in the first term. For the second term, the bracket operation which is entering here is what's called the Lie derivative of vector fields. So this operation on a smooth manifold takes two vector fields and outputs another one. Okay, so we can also extend this Lie derivative, which appeared in the exterior derivative definition for vector fields, to more general tensors, and then this is what it looks like if that tensor is a differential form. Right? So this the Lie derivative of a tensor of the differential form in this case can be related to the Lie derivative of the vector arguments as such. Okay, and then there's another operation we can consider called the interior product, which sends a k form to a k minus 1 form, so it decreases the degree by 1, and this is defined as such. So this involves a vector field x in the definition of this interior product, and it basically becomes the argument in the beta as far as the definition is concerned. Okay, so then for differential forms, we get this very nice identity relating the Lie derivative, the exterior derivative, and the interior product. This is what's called Cartan's magic formula. So it's saying that the Lie derivative of a differential form phi with respect to a vector field x is the exterior derivative of the interior product with respect to x of phi plus the interior product of the derivative of phi. Okay, so now none of these operations before required the data of a metric, but now let's talk about some which do. So we'll start with this pointwise notion of an inner product. So we have some metric g. We have differential forms of the same degree. And then what we do is we contract using the metric on the indices of the differential forms, and then this is an inner product. Okay, so using this inner product, we can define an operation on differential forms called the Hodge star. So if alpha is a k form, the Hodge dual of alpha is an n minus k form that for all beta satisfies the following expression. So this actually defines the Hodge dual. So you can see that in terms of this, the pointwise inner product is entering here. There's a volume form associated with the data of the Riemannian metric. This is an n-dimensional form on our manifold. And then this defines the Hodge dual. Okay. You can also, in coordinates, write out an expression just directly for the Hodge dual in terms of its original differential form. Okay, and then using the exterior derivative and the Hodge star, we can combine these in a particular way to get what's called the co-exterior derivative. So this takes a k form and sends it to a k minus 1 form by composing the exterior derivative and the Hodge dual in this particular way, and potentially with a choice of minus sign depending on the degree of the differential form and the dimension of the manifold. Okay, so now we get to a fundamental result for differential forms in the context of smooth manifolds, which is valid on any compact manifold with boundary. Right, so what this is saying is if alpha is an n minus 1 dimensional form, where n is the dimension of the manifold, then the integral of the exterior derivative of alpha, which is a top dimensional form over the manifold, is equal to the integral over the boundary of the manifold of the form alpha. Right, so this is valid on compact manifolds with boundary, and a particularly interesting case is when the manifold does not have any boundary, in which case the right-hand side of this equation is 0. So the previous part was Stokes' theorem, but we can use this to prove there's some useful corollaries of this, including integration by parts. So this is how we relate this to the co-exterior derivative. So this is saying that the integral of this expression here is what's called the L2 inner product of d alpha and beta on the left-hand side, which is defined using the pointwise inner product, is equal to the L2 inner product of alpha and d star beta. Right? So the proof just directly uses Stokes' theorem. And what this is saying is that the co-exterior derivative is the formal adjoint of the exterior derivative. Okay. So then another fundamental result in the compact setting is what's called the Hodge decomposition. So this says that on a compact manifold, we can uniquely decompose any K-form orthogonally into the following three pieces. So we're going to get what's called an exact piece. So it'll be a D alpha, a coexact piece, the D star beta, and then a term gamma, which is harmonic, which means it is both closed, so the exterior derivative of gamma vanishes, as well as co-closed, so the co-exterior derivative of gamma vanishes. So these harmonic forms are closely related to the topology of the underlying manifold via de Rham cohomology. And it's saying that all three of these pieces can potentially come up in the decomposition of any differential form in the compact setting. Okay, so lastly, I would like to emphasize that the Levi-Civita connection, which is frequently talked about in the context of differential geometry, is really the fundamental object under consideration in that case, can be used to express both the exterior derivative and the co-exterior derivative based on the following formulas, right? So the exterior derivative here can be written as such. This is taking the derivatives of the components here. This is how you get relating the components. And the co-exterior derivative similarly is involving a contraction in that case. All right. Okay. So this was basically an overview of some of the operations that you get for manipulating differential forms on smooth manifolds, both with and without the additional data of a metric. I'll be posting more videos on geometry soon, which will involve differential forms, so please stay tuned. Thanks.